evaluating world models remains a fragile practice. A scalar score tells you how a model performed, but it rarely explains why. When judging a rollout, you need to understand whether physics, causality, and world state evolve correctly. Humans spot violations naturally, yet existing benchmarks compute metrics in a brute force manner, leaving no reasoning chain that can be examined or verified. This paper introduces HarnessEval-W, an agentified evaluation pipeline that brings the harness paradigm from the LLM ecosystem to world model benchmarking. Rather than applying a fixed rubric, HarnessEval-W interprets the context of each evaluation case, decomposes the question into measurable subproblems, and spawns specialized subagents equipped with tailored context and diagnostic tools. The parent agent validates the gathered evidence and summarizes it into a final verdict. This hierarchical workflow turns every evaluation into a transparent evidence tree whose complete reasoning chain justifies the result. From a theoretical standpoint, the authors formalize an interactive world model as predicting future observations, conditioned on historical observations and user-specified actions. Given initial observations and future actions, the distribution of future observations is obtained by marginalizing the hidden states of the world model. This factorization exposes three fundamental abilities: rendering observations from the current state, updating the state under actions, and maintaining a coherent state sequence over time. Based on this decomposition, HarnessEval-W constructs three evaluation axes with 8 detailed settings. Observation quality assesses whether the rendered observation is visually reliable and physically plausible. Transition correctness evaluates whether the state transition faithfully executes requested actions, categorized into exploratory, intentional, and physical transitions. World persistence checks whether the sequence of predicted states remains coherent, testing drift resistance, revisit consistency, and off-screen evolution. The evaluation pipeline operates hierarchically to handle the context dependency of world models. It begins with case-specific skill routing. Based on the initial image and action prompt, the system routes the case to applicable skills from a predefined library. This routing depends only on the case context, ensuring the evaluation remains fair and unbiased across different models. Once a skill is assigned, the pipeline performs granular evaluation via subagents. For example, the intentional change verifier skill decomposes the problem into sub-questions answered by dedicated subagents. Target visibility, target specificity, whether the intended change occurs, final state validity, anchor preservation, and the absence of extra events. Each subagent scores the rollout against its specific expectation. The parent agent aggregates these outputs into a structured evidence tree. This design ensures that a low score can be traced back to a concrete failure, such as the wrong target being manipulated or an unrequested extra event occurring. To construct the benchmark, the authors developed an agentic case construction pipeline, as manual authoring does not scale while maintaining diagnosability. The pipeline samples an initial world setup from a structured scene taxonomy with 6 axes: environment, foreground, midground, scene density, appearance, and perspective. It then assigns a probe family, such as exploratory transition or off-screen evolution. An image generator creates the initial state. An image-grounded planner specifies concrete actions ensuring they are meaningful and diagnosable. And a case validator audits the pair for visibility, feasibility, and sufficient evidence. This process yields a benchmark of 330 evaluation cases, spanning diverse initial worlds and interaction patterns. The authors evaluated 18 representative world models, spanning general-purpose video generators and interactive world simulators. Seedance 2 ranked first with an overall score of 75.5, followed by WAN 2.7 and Kling 3. The advantage of text-driven generators appears to stem from large-scale text condition training, which supplies strong grounding for interpreting the consequences of actions. Crucially, HarnessEval-W's judgments align closely with human preferences. A human study using a Bradley-Terry model showed a Spearman rank correlation of 0.93 on intentional transitions and 0.87 on physical transitions. Compared to the closest existing protocol, W-Bench, HarnessEval-W significantly improves pairwise accuracy and reduces the draw rate, demonstrating that decomposing a global judgment into separately grounded sub-questions produces more discriminative and human-aligned evaluation. The system also exhibits robustness, producing consistent results across repetitions with a much narrower envelope of variation than baseline protocols. A key insight from the analysis involves capability shifts under fine-tuning. When text-to-video models are adapted into action-conditioned world models, capabilities redistribute rather than uniformly improving. For instance, fine-tuning WAN 2.2 into DreamX World improved drift resistance and revisit consistency, but caused a substantial drop in intentional and physical transition correctness. Similarly, HY World Play gained in revisit consistency, but lost significantly in intentional and physical transitions. This suggests that current fine-tuning data emphasizes exploration-style trajectories over commanded interventions, a trade-off that HarnessEval-W makes visible. Looking forward, the paper outlines directions for a self-evolving harness. This includes test time scaling for agentic benchmarks, where additional compute buys finer skill decomposition and deeper verification. It also proposes scaling skill libraries and creating recursively self-improving benchmarks that can acquire missing capabilities when encountering out-of-distribution scenarios. HarnessEval-W is open-sourced as a living benchmark, inviting the community to contribute new skills and evaluation cases as world models evolve.